Once we've selected or filtered our data, we often want to transform it somehow. The best way to transform data in Pandas data frames is with methods inherent to data frames. Next best is using NumPy ufuncs or universal functions to transform entire columns of data element-wise. Let's have a look how this works. Suppose we want to convert sales numbers into units of whole dozens, rounded down, rather than individual item counts. The most efficient way to do this is to use a Pandas built-in method like floordiv. Notice this arithmetic operation is applied to every entry in the data frame without writing any loops. Another way to do this uses NumPy's floorDivide function. Both of these strategies use vectorized or element-wise computation to repeat the same computation over an entire data structure without writing any loops. If Pandas floordiv and NumPy's floorDivide were not available, we could make a custom function to do this. Here, we call it dozens. The data frame apply method, called here using dozens, executes that function with each entry of the data frame, again without writing any loops. Yet another way to achieve the same result is to use a lambda function with the apply method. The lambda keyword, followed by the input argument, a colon, and the output expression, provides a convenient one-line definition of a throwaway function. All of the preceding computations returned a new data frame without altering the original data frame df. To preserve a computed result, we can create a new column storing calculations. For instance, here we create a new dozens of eggs column in which the floordiv12 method is applied to the series df eggs. Both apply and vectorize methods work on series as well as on entire data frames. Moreover, filters and indices often provide subset series or data frames for transformation. Having worked with vectorized computation of a numerical series, let's look next at string operations. Notice the df.index attribute is itself a special kind of series containing strings in this instance. Data frames, series, and index objects all come with a handy .str attribute as a kind of accessor for vectorized string transformations. Here, we assign the index df.index.str.upper to make the index all uppercase. Again, notice we did not loop explicitly over the entire index. Instead, we applied vectorized string method to transform the entire index element-wise. For the index, there is no apply method. For the index, the relevant method is called map, an unfortunately different terminology. Thus, we can apply, say, str.lower or a custom transformation to the index element-wise using the map method instead. Many arithmetic operators, for instance the plus sign, work with data frames and series directly. Thus here, we create a new column, salty eggs, by adding the salt and eggs columns together. If we can express a calculation using pandas alone, that's always preferable to using loops. That's an awful lot to absorb. Take some time now to work through the exercises using vectorized computations. We've already seen how to slice, filter, transform, and index pandas data frames. To learn more advanced indexing, we need to understand what indexes are. The key building blocks in pandas are indexes, series, and data frames. An index is a sequence of labels. Series are like one-dimensional NumPy arrays coupled to an index with fancy labels. Data frames are two-dimensional tables comprising series as columns sharing common indexes. Like the dictionary keys, pandas indexes are immutable. Like NumPy arrays, indexes are homogeneous in data type. Let's explore all this with an example from scratch. We construct a pandas series shares using a numerical list prices as the data. Printing shares shows a range of consecutive integers starting at 0 associated with each of the prices. Notice that the type of the series is float64, which is inferred from the numerical prices list. we now make a list days of weekday abbreviations to use as labels. We recreate the series shares, this time declaring days as the index. The new series has strings associated with its data instead of integers. We can see shares.index is of type index with data type object. We can index and slice from shares.index just as we can with Python lists. It also has a name attribute which has the value none. We assign the string weekday to the attribute shares.index.name. Now, when printing shares, that name is attached to the index. Notice an exception is raised when attempting to assign to individual index entries or index slices. Index entries are immutable, like dictionary keys. This restriction helps pandas optimize operations on series and data frames. It is technically possible to reassign to an index by overwriting it all at once. Notice that doing so also erases the name of the index. As a larger example, we load a data frame of unemployment data from the 2010 US Census. The columns are zip codes, unemployment rates, and numbers of participants. Notice, by default, the index for the data frame contains consecutive integers starting at 0. Using the info method shows more detail. The index is in fact a range index from 0 to 33,119. This data frame, then, is indexed exactly as a NumPy array. It's better to use the zip codes column as an index instead. After all, they are identifiers for this particular dataset. We can assign the column zip to the attribute unemployment.index. Now, the index contains the zip code data, as does the column zip. We can delete the redundant column using del. The result is a data frame with only 2 columns indexed by the zip code. Printing unemployment.index shows an abbreviated index. Its name attribute is the string zip inherited from the former column. The index is itself of type int64 index and contains an unsorted list of non-consecutive integers. Looking at unemployment.columns reveals it is also an index of type object. It's worth pointing out that we could have got the index right from the start. The trick would have been to use indexcol equals zip to tell readcsv which column to use as the index. Take some time now to work on some exercises to familiarize yourself with indexes. Knowing how indexes fit with pandas data frames and series, we can now look at representing multi-dimensional data with hierarchical indexes. Let's motivate this with some stock data. Here's a data frame with some Apple, Cisco, and Microsoft stock trades taken over 3 days. The columns are the date, the closing price, the volume traded, and the ticker symbol on the stock. Notice the default index is an integer range. The rows are not sorted sensibly. There are repeated values in the date and symbol columns. We would prefer using a meaningful index that uniquely identifies each row. Individually, both the date and the symbol columns are inappropriate due to repetitions. The trick then is to use a tuple, symbol and date, to represent each record in the table uniquely. We use setIndex with an ordered list of column labels describing the new index. When we print stocks now, the index is no longer a range of integers. Instead, the index comprises 2 columns, symbol and date. Of course, the data frame is still unsorted. We print out and examine the new index. It is a multi-index or a hierarchical index composed of the entries from the original symbol and date columns. Notice when we print stock.index.name, the result is none. When we print stock.index.names, the result is the list symbol, date. We need to call sortIndex to sort the data frame. Again, we assign the output of sortIndex. This makes a new data frame in memory. Printing the sorted data frame shows the multi-index labels in a readable, ragged form with gaps where the symbols AAPL, CSCO, and MSFT would be repeated. Sorting a hierarchically indexed data frame is useful for indexing and slicing. For example, calling the .loc accessor with the tuple CSCO, 2016-10-04 extracts the fifth row of the sorted data frame. If we follow the tuple with a column name, say volume, we can extract a single element of the table. Calling the .loc accessor with the string AAPL alone slices on the outer index, returning all rows corresponding to AAPL trades. We can also extract a slice using a range of symbols. As an example, say CSCO, MSFT. This extracts the bottom 6 rows of the sorted data frame. Fancy indexing, or using lists in indexing, is also possible. We can slice the rows for AAPL and MSFT data on October the 5th, like this. And if we want only the close columns on those days, we do this instead. Fancy indexing also works on the inner index. Here, we pull the CSCO rows from October 5th and October 3rd in that order. There's a trick to slicing with hierarchical indexes. The tuple used for the index does not recognize slicing with colons natively. To force that to work, we need to use the Python built-in slice explicitly. For example, here we use the tuple slice none, slice 2016-10-03, 2016-10-04 to extract rows from all symbols for the dates October 3rd through 4th inclusive. It's a good idea to practice this. Try the exercises now to get used to multi-indexes and hierarchical indexing.